Hi everybody, welcome to Module 2, and we've finished Module 1. You should have everything in Module 1 done. We're now moving into Module 2, and in Module 2, this lecture is one of the most important lectures you will ever watch in your life, because in this lecture you're going to learn how computers work. So you're going to learn about the basic functions of a computer, and you're also going to learn why computers have all those zeros and ones associated with them. So we're in module number 2. This is a great lecture. I really encourage you to watch all of it. You're going to get some fantastic information in here. And so we're going to start out. We're going to start out by looking at the learning objectives for module 2, chapter 2. And we'll go through these in a second. And then once we've gone through these first 2 slides here, we're going to jump over to my own PowerPoint presentation. You're going to learn how computers work. And then we're going to come back here and just briefly go through everything in the rest of this chapter PowerPoint presentation from the textbook. So that's the game plan. Super important lecture. I'm glad you're here. Grab a nice beverage, maybe a little popcorn, just relax on the couch and hang out with me here for a little bit while we learn some really important information. And what you're going to learn in this lecture is going to be it's going to differentiate you from the vast majority of people in humanity. You will have a solid understanding of how computers work by the end of this lecture. All right, so the first thing we're going to talk about are the 4 main functions of a computer system and how they interact with data and information. And so the 4 main functions of a computer are that they do these things IPOS, and that acronym IPOS stands for input, processing, and output and storage. And the reason we have computers is so they could take data and they could turn it into information. So we're going to talk about all that. So the first thing is what are the 4 things a computer does? Input, processing, output, and storage. If you think about your own mind, if you think about your mind like a computer, let's do a little bit of a thought exercise here, a little bit of an experiment. Are you ready? So I'm going to give you a math problem. Here we go. 2 plus 3 equals, and so when you hear all of that, you're like, okay, 2 plus 3 equals 5. Well, in that process, if you break it down, you realize you received input. I gave you 2, I gave you plus, I gave you 3, I gave you equals. You received input through your ears and also visually, you're watching this. And then you also, I'm just going to make sure I'm recording. All right, good, we're recording. You also, while you were receiving input, you were storing that input. You were remembering it. You were remembering 2, you were remembering plus, you were remembering 3. And then when you heard equals, you processed that. You're like 2 plus 3 equals 5 in your head, right? And then if we were talking, if we were having a conversation, you would have output that information. You would have said 2 plus 3 is equal to 5. The answer is 5, right? So the 4 basic functions that you went through for the processing machine, which is your mind, use these 4 functions. You had to receive input. You had to store that input as it came in. You then process that input, and then you output the answer. And so those are the 4 main functions that the brain kind of does when you're interacting with the world. You're receiving input. You're storing input. The brain actually filters out the vast majority of input that's coming towards us. It's like a funnel that reduces all of the input, just an interesting tangent, and only shows certain things to us. And also interesting about the brain is the brain works with heuristics or rules of thumb, where it really quickly labels things as known. And when you think you know something, then you don't have to contemplate it. You don't have to spend processing power on it. Like this is a hat, right? As soon as you see it, you're like, hat, I know what that is. Or this is a pen, or this is a screwdriver, right? So that's how the brain works. It filters things out and just uses heuristics, rules of thumbs. But the main point here that we're learning is IPOS. Those are the 4 functions that the brain goes through when it's interacting with the world. Those are also the 4 functions of a computer. So the first person to come up with this idea, if you think back in time, before computers had existed, to come up with this idea of creating a machine. It's a machine. To come up with this idea of creating a machine that could process like the brain, you had to think about these 4 functions that the machine's going to do. It has to receive input, it has to be able to store that input as it's received, and then it's going to process that input, and then we could produce output to get an answer. And so Charles Babbage came up with this idea for a difference engine or an analytical engine or analytical machine. and he never saw it come to fruition. The machining to create the gears and things like that wasn't fine enough, precise enough at the time that he lived in the 1800s. But he created blueprints for it, and then later, you know, in the 20th century, in the 1900s, maybe it was actually in the 21st century, in the early 2000s. Somebody took those blueprints and recreated or created for the first time his difference engine, his analytical engine, and they put it up at the Computer History Museum in Mountain View, California, which is just 2.5 hours from here. And so here it is right here. You can see it. I'll link this video in our course module number 2, so you can take a look at this video. It's a great video, but you can see right there a little bit of insight into that difference engine and what it looks like. It's this mechanical machine that receives input. It could store the input it receives. It could then process the input, and it can produce output. So IPOS, input processing output storage. So the next person that was like really significant in the development of a computer is a guy named Alan Turing. And so Alan Turing, there's a movie about him called The Imitation Game. And The Imitation Game is a great movie. It's going to be one of our discussions. So if you see in here, we have different discussions. And so somewhere down in here, we probably have The Imitation Game. I believe that's in there. And Snowden, The Imitation Game right here. So down in module number 11, this will be something that hopefully you'll be able to watch. And then you could comment in the discussions. If nothing else, at least watch the trailer. But it gives you insight into a really brilliant man, one of the most brilliant minds of the 20th century, of the 1900s, Alan Turing. And he knew, I speculate this because he was also from Britain, from England, but he knew of the work of Charles Babbage, and then he built upon that. And then he built not a mechanical machine to do input processing, output, and storage, but he built an electrical machine that could do input processing and output and storage. And he's the first person to do it, and he built that at this place called Bletchley Park. And Bletchley Park is in England, so here you could see it. And it was a secret place during World War II, and you could see that there's a little bit of encryption going on there as we were bringing this up. And it's just like jumbled words and letters. This is really cool that Google did this, but then it became unjumbled, because what Alan Turing did during World War II at Bletchley Park was he invented an electrical machine which could crack German encryption every day consistently without error. And that was a phenomenal accomplishment. It's one of the huge milestones in the history of humanity. And because of that, the Allies were able to defeat the Axis powers. I think I'm saying that right? Let's see. ChatGPT. We have the Allies in World War II. Tell me briefly about the Allies and the Axis powers. Is that what they're called? All right, so we're going to find out here, because I was not totally sure about that. Yeah, the two major opposing military alliances were the Allied powers and the Axis powers. So the Allied powers were these people, and the Axis powers were these people. So that was World War II. But anyhow, the Allies were able to beat the Germans, basically, and it was because of Alan Turing creating this machine. So Alan Turing was incredible and a brilliant mind, and it's a great tragedy. His life was a big tragedy, and we lost one of the most brilliant minds in the history of humanity, because he was also homosexual, and at the time that was illegal in Britain, and he got persecuted for that and put on hormone therapy, and that either led him to be suicidal or somebody killed him because of it. So a real tragedy. All right, so that's IPOS, input processing, output, and storage. And we have machines that could do these 4 functions, so that we could take data, the processing part of it, we could take data and turn it into information. And so the way computers take data and turn it into information is, imagine what the world was like before computers. So let's say that you had, there's 10 restaurants around you, And every restaurant, customers wrote down on paper some feedback about the restaurant and left a rating of 1 to 5. You know, like how well did they rate it, 1 to 5. And so you have 10 restaurants, each with 1,000 pieces of paper with a review and some sort of a rating. That's 10,000 pieces of paper. That's a lot of data. If you enter all that data into a computer, you can process it and turn it into information. You can know the average rating for each restaurant. You can know what is a synthesis of all of the written comments about that restaurant. And today we can see pictures of the food. We can see pictures of the menu. We can see pictures of the interior. We can see where the restaurant's located. We could get directions to the restaurant. We can see when is the restaurant open. We could get all of this information from all of the data that people have entered. So computers take data and turn it into information. So also what we're going to learn in this chapter is we're going to learn about bits and bytes and describe how they are measured, used, and processed. We're going to list common types of computers and discuss their main features. We're going to identify the main types of keyboards and touch screens, and we're going to describe the main types of mice and pointing devices. We're also going to explain how images, sounds, and sensor data are input into computing devices. This is all at a very general introductory level. And we're also going to describe options for outputting images and audio from computing devices. We're going to describe various types of printers and explain when you would use them. And we're going to describe the functions of the motherboard and RAM and explain the main functions of the CPU. And then also describe means of storing data and information within computing devices. Describe common types of ports used today. Describe how to manage power consumption on computing devices and define ergonomics. And discuss the ideal physical setup for using computing devices. So all that is coming. But first, we're going to jump into this and see really kind of at a basic level how the computers work. So we'll go over all these things here. So the most important thing you need to know, there's 3 important things to know about computers so that you can understand how they work. And the first thing to know is that computers run on electricity. The second thing to know is that electricity has 2 discrete states, on or off. Now discrete is separate, and I'm saying discrete there. Discrete is separate from continuous. So continuous would be like lights that are on a dimmer. There's an infinite number of settings from off to on, right? For a light that's on a dimmer, infinite number of shades, infinite number of points between on and off. And interestingly, with quantum computing, that's more like how quantum computer works. It's not just on and off, but there's states between on and off. But with current modern day computers, these computers, they run on electricity, and then 2, they take advantage of this idea that, and this property of electricity, that electricity can be on or off. So that's the first thing to know, is that they run on electricity. The second thing to know is that electricity has 2 discrete states, on or off. And then the third thing to know is your porch light on Halloween. So computers are like your porch on Halloween. Porch light. We'll say porch light. Your porch. Computers are like your porch light on Halloween. So that's the next thing to know. That's interesting. So if you think about your porch light on Halloween, you've got a light out there, right? And that light can either be on, or it could be off. And if the light's on, it means come trick or treat. And if the light's off, it means go away. So with one light, with one switch, you could flick the switch on, you could flick the switch off, or one circuit, the circuit could be on or the circuit could be off. With one light, with one switch, with one circuit, all those are synonymous, interchangeable words, light, circuit, switch, light, switch, circuit, right? All those are interchangeable. With one light, one switch, one circuit, I'm just trying to remember them in the order I'm saying them, you can store and convey 2 pieces of information. If the light is on, right, with one light, you could say, hey, that means come trick or treat. So we'll put this here, come trick or treat. And if the light is off, go away. So with one light, we have input information. We turn the light on or off. And then we've also stored that information. The light stays on or the light stays off. And we're also outputting that information. If the light's off, it means go away. And if the light's on, it means come trick or treat. And all of this is known as a coding scheme. So here's the idea about how computers work. If you have some switch, if you have some circuit like a light, you could create a coding scheme for the different states of that circuit, that switch, that light. And if the state is on, it can mean one thing, and if the state is off, it could mean another thing. Now there's a couple pieces of terminology in there, and that could seem a little bit confusing when you're first exposed to that idea, but at a very basic level, that's a really simple concept which you really understand. It's your porch light, on Halloween, right? That's what a computer is. It's just like your porch light on Halloween. It is a circuit or a switch that could be in an on-off position, and based upon whether or not it's in an on-off position, you could apply a coding scheme to that. So if it's on, it means one thing. If it's off, it means something else. Now, amazingly, that's exactly how computers work, but at a really, really, really large scale. And we'll see that coming up, how big of a scale that is in a second. So let's just explore this idea of using circuits or switches like a light to store and convey information with a coding scheme. And so if we had two lights on our porch, how many messages could be stored, right? We could store 4 messages. It could be off and off, or off and on, or on and off, or on and on. These are the different states those lights could be in, different combinations of off and on. And based upon their combinations of off and on, we could come up with another coding scheme. We could just randomly create a coding scheme, and we could tell people about it. We could say, hey, if my porch lights are in one of these 4 states, this is what I'm trying to convey to people. And if we've told people this coding scheme using circuits, switches like lights in on-off states, we're able to input, store, and output information to people. That's amazing, right? So that's if we had 2 lights. What about if we had 3 lights? How many messages can be stored or conveyed in our coding scheme? With 3 lights, we could have 8 different combinations of on or off. And so when we create a coding scheme, we could have 8 different, messages that we could store and convey to people when they see our porch lights, our 3 porch lights in a different combination of on or off. If they know this coding scheme, they understand, what's going on. And this last one, I'm going to change it, and I'm going to put new kittens. I don't know. Why not? Because my family's got new kittens, so that comes to mind. So there's with 3 lights. And if we wanted to, instead of writing on or off all the time, we could just use 0 in notation for off, and we could use 1 for on. So off, off, off would be 0, 0, 0, or off, off, on would be 0, 0, 1. The 0 is off, the 1 is on. And so we could just write those 0s and 1s. Instead of writing all the off and on, we could just have it like that. And so that's where 0s and 1s come from in computers, is that they are representing these states of off and on. And so that's an illustration of that right there. And instead of having just some sort of like, I don't know, silly coding scheme, we could have those 0s and 1s represent letters of the alphabet. So when somebody pushes the letter capital A on their keyboard at a computer, inside the computer, we could just have switches or circuits go into some sort of an on-off state. And so for the letter A, it'd be 3 in this coding scheme here that we're just creating. In the letter A, it would be 3, I'll make that yellow so it's not confusing. It would be 3 circuits or switches in the off state. For the letter C, it would be 3 circuits or switches, 1 off, 1 on, 1 off, and that's the letter C. So if we gave somebody some 0s and 1s like this right here, they would then be able to, we said, hey, here's a circuit that is in 3 circuits that are in 0, 0, 1, off, off, on state. They'd be able to see that, and they'd be able to say, oh, that's the letter B, or this is the letter A, or this is the letter D. And they'd be able to decode the message based upon the states of these circuits or switches. They'd be able to associate that with some meaning, right? And so here, that's all I could come up with these 8 letters of the alphabet, but that's how it works. And so that's really the fundamentals of how computers work. Inside a computer, there are all these circuits or switches that can be in on or off states. And based upon whether or not they're in an on or off state, there's some coding scheme that tells the computer what that on-off state represents. It might represent letters of the alphabet, right? And that's literally how letters of the alphabet are stored in a computer. They're stored with more circuits or switches than just 3. The original computers used 8 circuits or switches, and we called 8. And by the way, we call these zeros and ones. We call these zeros and ones here. We call them binary digits. And because it's a binary digit, because, well, 1, it's binary, right? 0 or 1, or 1, these are digits, right? And then it's binary. So binary means like it has the prefix bi, and bi means like bicycle, biplane, and binary means 2. Okay, so it's 2 digits, and we abbreviate binary digits as bits. So when you hear about bits, we're really talking about zeros and ones. And the reason we're talking about zeros and ones is because that's shorthand notation to represent off and on. And the reason we talk about off or on is because computers run on electricity, and electricity has 2 discrete states. And when we have electricity with 2 discrete states, we could start making coding schemes. And just like our porch light on Halloween, on can mean come trick or treat, and off can mean go away. And so we have this idea, this is how computers work. They run on electricity. Electricity can be on or off. And with a circuit or a switch in an on or off state, we could create a coding scheme to represent, if the circuit's in this state, it means this thing. If it's in that state, it means that thing. This could be a nonsensical kind of silly example where it just means come trick or treat or go away, or it could be letters of the alphabet, or it could be sounds, or it could be colors. So an image on your screen is made up of little dots of color. It's like pointillism in art. There's little dots of color. Those little dots are called pixels. Those pixels are picture elements on a screen that is normal HD definition. There's 1980 by 1024. So width, there's 1,980 dots left to right. And then there's 1,024 rows vertically from top to bottom. And so there are 2,027,520 of those little dots or pixels. What I'm saying is pixel here, pixel, right? Those little pixels. So pixel, Wikipedia, right? So pixel, Google Pixel. Here's a pixel. In digital imaging, a pixel picture element is the smallest addressable element in an image. So it's that little dot that could be a color. And so each of these pixels has like a certain number of binary digits of bits representing what color should be shown at each of these dots, right? So if it was like some combination of on, off, on, that might be the color pink. And the computer then looks at each pixel. What is the bit depth? What's the color depth? What are those bits representing a color? And it says, okay, this one little dot needs to be this color, and it does that for all these dots. Like these little pixels here are red with some white pixels in the middle right there to make that little YouTube arrow, and it stores that information for every single picture element, every single pixel on your screen. Now the original computer monitors, so black green computer screen, right? The original monitors back when I was a kid, they were like this, because for every pixel, it could be either black or green, so that for each pixel, they were storing 1 bit of information, 1 binary digit on or off, right? It's less data. Earlier computers weren't as powerful, obviously, and so they had less data, so your screen is black or green, right? Like this is back in the 70s and the 80s. And then that's what computers could process at that time, because we hadn't figured out and engineered how to make them more powerful. And so that was the color depth or the bit depth, color depth, bit depth, right, of the image of the monitor. And you could pause this and read about this. And so the bit depth was 1. Each pixel had 1 bit, 1 circuit, 1 switch that could be in an on-off state to represent if it's black or green. Today they might have 16 or 24 or 32 bits for every pixel. So, if we had a computer that had, 24 bits, times 24 for each pixel to store 1 image that's HD with no compression, we're going to store 48,660,480 circuits in on-off states to represent all the colors in that screen. So that starts to give you an idea of like how powerful computers are. It's all like your porch light on Halloween, right? It's all circuits or switches in some on-off state, and then we associate that on-off state with a coding scheme. And for colors, we say, okay, if it's in this arrangement of on and off, it'll mean this color, and we're going to apply that color to this pixel. We're storing 48,660,480 circuits, switches in on-off states to store all this information that you're seeing on the screen right now in an uncompressed fashion. So there is compression, and we call this compression, decompression algorithms, okay? And we abbreviate that as a codec because codec is, right, that's the first part of compression, and this is the last part of compression. And so there are ways for us to reduce the amount of data, amount of circuits and switches that need to be in on-off states. We could reduce that data by having compression and decompression algorithms. And just to illustrate that, if we wanted to store the image of a German flag, we could have a mathematical formula that says, hey, from this point here to that point there, all the same color yellow, right? Like we don't have to worry about storing yellow for each one of these dots. We'll create like a JPEG or a PNG. It has a way to unpack the information that's been stored. And part of that will be to say from here to there, all the same color yellow. And so then we could just paint that in. We don't have to store that data for every single pixel. So whether it's like, you know, a letter of the alphabet, whether it's a color on your screen, whether and for video, by the way, you create an image and you show 24 or 30 images a second. And so, right, without compression, if we were to store, you know, 24 frames per second, so, you know, this is how many, the bit depth of each pixel. This is how many pixels for HD right here, 1980 by 10,024. And then we store this many circuit switches and on-off states for each pixel element. And then we have 24 of those pictures every second to be a movie. So for 1 second of a movie, we're going to have 1,167,851,520 circuits or switches in on-off states to represent 1 second of a movie in completely raw, uncompressed fashion. And so because that's a tremendously large number, we figured out how to compress, or people have figured out how to compress, humans have figured out how to compress that so we could send less data over the wire because, and have less storage when we're storing a movie. But this is how we store letters of the alphabet, colors that you see on your screen. This is how we store movies. This is how we store sound. So for sound, CD quality is 44,100 samples per second, and they call that hertz. Kilohertz, 44.1 kilohertz. And so every second with sound for CD quality, they're taking 44,100 samples, and each sample will be a certain sound. Just like a pixel will be a certain color, each sample will be a certain sound, and we'll have zeros and ones, circuit switches and on-off states to represent that sound. And we'll have 44,100 of those individual sounds that we play right next to each other in 1 second, and it'll come out sounding like this. It'll sound like my voice. It'll sound like somebody singing. And that's how sound is stored in computers. It's all circuits and switches and on-off states. And that's why in this movie, The Matrix, and if you've yet to see The Matrix, it's a super deep movie, philosophically profound. But that's why, you know, in the movie The Matrix, it's a great movie. At the end of it, like it's all like a hologram. It's all a computer simulation. And at the end of the movie, Keanu Reeves, who's the protagonist in the movie, realizes this is all computer code. And he becomes computer code in the system because that's, you know, where he's at. It's all this hologram that he's walking through. And he masters the system by just being able to realize it's all zeros and ones. They use a slightly different green, you know, not just the zeros and ones, slightly different notation to represent that. But that's how the movie ends, and that was his great insight at the end of the movie. So super fun movie to watch. So that's how computers work. That's how computers work. And that's why computers have zeros and ones, and that's why we, talk about binary digits or bits, and that's why, the power symbol looks like this. This is the power symbol. It's a 0 and it's a 1. This is how you turn a computer on or off. On is 1, off is that 0. That's amazing, right? So the zeros and ones, like most people have never looked at this symbol and seen that before, but those zeros and ones, which represent circuits or switches that could be in on-off states, right? It's not that there's zeros and ones like pulsing around in a computer. They're electrical impulses of on or off that are pulsing around in the computer. We represent those circuit switches, those electrical impulses of on or off. We represent those as zeros and ones, as 0 and 1. 0's off, 1 is on. So that's how that works. And if you have like a terabyte of information, so I'm just gonna like copy this here, if you have a terabyte of information, so you have, first of all, let me just bring this up here. First of all, and bring this down here. And let me make this a little bit smaller. Make it 30. We'll make it 18. There we go. All right. And let me make that left aligned, and I want it to be top aligned. How do I get top aligned? I don't know. I think I have the wrong one for that, but this will work. All right, so we have 1 bit. And then if we have 8 bits, we call that a byte. And that's significant in computer history because the original computers operated with registers or places of memory, which were 8 bits or 1 byte. And so letters of the alphabet were stored with 1 byte. And those original bytes, the original coding scheme for storing letters of the alphabet, was ASCII. And so you could come in here and you could see ASCII. And so the letters of the alphabet were stored with an arrangement, I'm just looking for one that's easy to interpret, of zeros and ones. And so you could see A was 65. And we're going to learn how to count in binary. And you'll be able to, at some point later in the course, understand like how do you get the decimal value of 65 out of the binary value of zeros and ones. But that's the circuits in on-off states that would have represented the capital letter A, and the lowercase letter a would have been represented by 97 in decimal. And again, there's a binary representation of the decimal numeric representation of 97. There's a binary representation, right? And so here you could see kind of the translation to zeros and ones of different letters of the alphabet. So we'll see that. We'll see that coming up later in the course. So we have 8 bits or 1 byte. The original computers were using 8 bits to store letters of the alphabet, and that was referred to as a byte. And then after 1 byte, if we had 1024 bytes, that was equal to 1 kilobyte. And we called that a KB, right? That's referred to as a KB. And if we had 1024 KBs, kilobytes, that is equal to 1 megabyte. And we call that a megabyte. And if we had 1024 megabytes, that is equal to 1 kilobyte, megabyte, gigabyte. And if we refer to that as a gigabyte. And if we have 1024 gigabytes, that is equal to 1 terabyte. And that we refer to that as a TB. So if you have 1 terabyte, so if we have 1 terabyte, that is equal to 1 terabyte. 1 terabyte is equal to, and I got to do it like this. 1 terabyte is equal to 1024 gigabytes. Sorry, let me do this over. I kind of need to draw it out. I'm just thinking about how to do that. Hold on 1 second. Let me do this math and then I'll restart this video. All right, so I just thought of the easiest way to do this is I'm going to go to ChatGPT and I'll start a new chat over here. And I don't know what's on that one. And so I'm going to say, can you please show me the math with cross cancellation to convert 1 terabyte to bits? Perfect, way quicker. Step 1, convert terabytes to gigabytes. 1 terabyte is equal to 1024 gigabytes. Convert gigabytes to megabytes. 1 gigabyte is 1024 megabytes. Step 3, convert megabytes to kilobytes. 1 megabyte is equal to 1024 kilobytes. Step 4, convert kilobytes to bytes. Step 5, convert bytes to bits. And so set up the cross cancellation. So this is what I was going to try to do on the PowerPoint slide, but that's hard to do. And so here we have 1 terabyte times 1024 gigabytes, and then terabytes cross cancel out here, and then the gigabytes cross cancel out there, and then the megabytes cross cancel out there, and then the kilobytes cross cancel out there, and then the bytes cross cancel out there. So you have 1 times 1024 times 1024 times 1024 times 1024 4 times, 1, 2, 3, 4 times 8. So 1 terabyte is equal to 8,796,093,000. Oh, sorry. So that is your millions. This is your billions. This is your trillions. 1,796,093,022,208 bits. That's what 1 terabyte equals. So you could store circuit switches in on-off states, this many of them, on a 1 terabyte drive, which is amazing. And this is so cool. I'm going to go and do my snipping tool, and I'm going to say new right here. And then I'm going to snip that right here, just like that, and that copies it into memory. I could also click save right here if I wanted. And then I'm going to come back over here, and I'm just going to bring this up and up. And then I'm going to click away from it and do V, and then there we have that. That's perfect. I really like that. So that's a little bit about bits and bytes, and why we call them bits. They're binary digits, and binary digits, bi means 2, is 0 and 1. And why 0 and 1? Because computers run on electricity. Electricity can be on or off. And when we have a circuit or a switch, like a light, that can be on or off, we could apply coding schemes to it and have those on-off states represent things, whether it's letters of the alphabet, whether it's colors for each pixel element on a screen, whether it's sound, right? 44,100 samples a second for CD quality. Those circuit switches and on-off states can have coding schemes where that arrangement of those circuit switches and on-off states has some meaning. And then the computer processes all of that really fast. And so a computer, like if we go to Costco, just to illustrate this, and we look at Costco, and we go to shop, and we look at shop, and we go down here to computers, and we look at the computers. I want to shop by category, desktop. I'm going to go for PC gaming, and then PC gaming, I want gaming desktops, and then gaming desktops, I'm going to sort them price high to low. And then here we have Intel 4th generation 24-core processor. I'm just looking to see what the gigahertz is for $2,800 bucks. I want to see what the gigahertz is and specifications. And I'm just looking to see if I could find the gigahertz on it. Hold on one second. Let me look for it. So I'm not seeing it on this screen, but I'm going to copy the processor type and then go back to ChatGPT and say how many gigahertz does operate at. It's 2.5 gigahertz to 3.8 gigahertz, and then I'm going to say, what does GHz mean? So gigahertz is the number of processes that a CPU can do in a certain period of time. It's the clock speed at which the computer is operating. And so 1 gigahertz is equal to, here we have millions, here we have billions, 1 billion things a computer can do in a second. And so if this is like 2.5 to 3.8, if it's 3.8 gigahertz, it could do 3.8 billion processing transactions a second. And so that's how fastly it's processing those zeros and ones to show you video, to like play audio for you, to display things on your screen. That's how quickly it's processing those. So it all comes down to these binary digits, circuits and on-off states, and then we have the different generations of computers where we are storing these circuits and on-off states. And so let me just look for that. I think that's up here. Just one second. Yeah, here we go. So the first computers used vacuum tubes to store on-off states, and the second, you could Google these to see what they look like. They're kind of interesting. The second generation computers use transistors to store circuits or switches in on-off states. The third generation of computers use integrated circuits or chips to store circuits in on-off states. Fourth generation computers began in the early 70s, and they had CPUs. And then fifth generation computers is, people speculate, artificial intelligence. And so that's what we're entering right now. And so you can see that, I guess I'll just show you vacuum tubes, right? So here is the first generation computers. These are about the size of a light bulb, but they could store on-off states and they could be checked. And then second generation of computers use transistors. And so you could see that's what they look like here, and they were much smaller. And I'm going to put in vacuum tube also versus vacuum tubes, so you could compare them. So you could see that's actually not an accurate representation. Here's a better representation of size. But they were much smaller, they ran cooler, they didn't burn out. So this was like, the first ones right here, and then, what they look like at different years. And the vacuum tubes in computers didn't come about until the mid 1940s, early 1940s. So that's just an early representation of a vacuum tube. And then the third generation, fourth generation. Third generation used integrated circuits or chips. And so here's what a silicon wafer looks like with chips on it. So let me just show you an image of that. And so you could see here, each of these, well, that was actually a really good one right here. Each of these little squares, this is a silicon wafer, and each of these little squares is an individual chip, okay? And a silicon wafer is about the size and thickness of your thumbnail. And I'm just looking to see if there's a picture of somebody holding one, so you could get a sense of like how thin it is and how big it is. But each of these chips is about the size and thickness of your thumbnail. And so you could go to Wikipedia, transistor count, wiki. And at Wikipedia, you can look at the transistor count, and on something the size and thickness of your thumbnail, the original computers could have about 2,000 in the early 70s. They could have about 2,000 circuits or switches that could store on-off states. Today's computers have, millions, and that's billions. They have 50 billion circuits or switches that could be stored in on-off states. 50 billion. So they're pretty extraordinary. And that's those are today's computers. So that's about how computers work. Those are the main things you need to know from my presentation. And then the rest of this information here in the textbook presentation goes through a few more details about how computers work. So we've learned about bits and bytes, and we've learned how they're measured and how they're used. And then the way they're processed is it's all electricity running through your computer. Listing common types of computers, we can look at that real quickly. So we talked about input, process, output, and storage. You can pause the video, see how the textbook talks about it there. We talked about bits and bytes, kilobytes, megabytes, gigabytes, terabytes, and then petabytes would be 1,024 terabytes. And then computers are found everywhere today. You can pause the video and look at this. And that talks a little bit more about bits and bytes and gives you some perspective on that. It's kind of interesting. And then there's different parts of a computer. So I used to think there was different types of computers, but any computing device is a computer, from your watch to your phone to your laptop to your desktop to things that are embedded like in your AC, your air conditioner, or your little panel where you set the air conditioner temperature. Those are embedded computers, to mainframes, to supercomputers. They're all computers. They all take input, processing, output, storage. They all have some sort of central processing unit, which is what CPU stands for, where all the processing occurs. They have a way to do the input. They have storage or memory, right? Here's a microphone for input, a camera for input. So all computers are computers. They're just different sizes, but they all do the four basic functions. They all do input, processing, output, and storage. So some of the different computers out there are like tablets and laptops. And then here's like, some of the, smaller to a little bit bigger of the computers. And then we get to even bigger computers like desktops. We get to even bigger computers like mainframes or supercomputers. But then embedded computers are just embedded in other machines. So here's like a supercomputer, it looks like right here. And those are like the biggest computers used for business and scientific research. Mainframes would run really large businesses, Fortune 500s. And then we have input devices. How do we get input into the computer? So there are some input devices. Here are more input devices. Here are more input devices. You can pause the video and read those. More input devices for getting data into a computer so we could turn it into information. And then we get information out of a computer. So here are output devices from computers, more output devices, more output devices, more output devices. You can pause the video and look at all those. More output devices, more output devices. And then we have to do processing in the computer. We'll learn a little bit more about this as we go through the material. So next week we'll talk a little bit more about the motherboard. So just like a mom in a family, a good mom connects everybody in the family, the motherboard in the computer connects everything in the computer. The motherboard does. And you plug the CPU and the storage, the memory, your solid state drives, your hard disk drives. You plug all of that in here. Random access memory is your memory. We'll learn about that next week. And your ROM, read-only memory, and your cache. We'll learn about that next week. And then we have the CPU, and that's where all the processing occurs for those four basic, the four basic functions. One of them is processing. So the CPU is the brains of the computer, and it operates at billions of tasks a second, like 2.5 to 3.8 billion tasks per second. And then here's a little picture of a single core versus a dual core or multi-core. So when you have a multi-core CPU or multiple cores on your CPU, it just means a lot of processing could happen at the same time. It's like you have multiple CPUs. You literally have multiple CPUs on your computer. And then we could store information with hard disk drives and solid state drives. You can see a picture of a hard disk drive here or a solid state drive here. Or there's like thumb drives or SD drives right here, SD cards. And so that's another way you could store stuff. And then there's cloud storage where you store things on other people's computers. And then we have different ports and cables, USB-A, USB-C. And you could Google that, USB-A versus USB-C, to just see what's the difference between those. But it's just different ways to plug stuff into a computer. So here's USB-A, here's USB-C. Right? And then here's USB-B, different ways to plug things into a computer. And I'm just making sure it's still recording here. And then finally, we have power management. So in your computer or on your phone, you could go in and set your power settings to burn more or less electricity. And then we have ergonomics. So ergonomics is designing places and machines and environments to work well with humans. And to have good ergonomics with your computer is really important. We'll talk about this a little bit more further into the class. But basically, if you look at how I'm sitting here, so let me just angle that video down, right? Like here I am with my laptop on my lap, or my keyboard on my lap. And the reason is because here my arms are hanging naturally. It's like just hanging, they're relaxed. They're not up here like this, they're not like that. They're hanging, they're relaxed. This is good for my body. It's the way my body's supposed to be. If you're like this all the time, you're going to get muscle pains, okay? And so hanging like this, relaxed. I got this little board here. I could type right here. This board's big enough for my mouse, so I could do my mouse right here. You can see in the little picture there. I'm doing my mouse right there. And I'll get away from that multiple input one, but and then I even have this little thing down here for my feet. And so here's this for my feet. So I put this under my feet to kind of bring my legs up a little bit. And let me just make sure that that image looks good. So you saw before and then after. So my legs are up. I'm sitting here, right? It's like my shoulders are relaxed. And I can get to my mouse real easily. Like this is good ergonomics. I'm not putting pressure on my carpal tunnels right here, which could lead to an injury, carpal tunnel syndrome, where you have to get surgery and you lose the functionality of your fingers if you get carpal tunnel syndrome. So you don't want to have pressure. You don't want to have pressure on your wrists. And so sitting, like I was sitting, is how you sit for good ergonomics. And your monitor should be straight out or a little bit down. You shouldn't be looking up. You should be looking straight across or a little bit down so your neck doesn't get sore. And that'll keep you safe using computers. And then we also have assistive and adaptive technologies to help people do things more quickly, talk into your phone, voice recognition, things like that. All right, so it's a little bit fast there at the end, but we covered all that information. And the most important thing you need to learn was how computers work. And they run on electricity. And electricity can be on or off, 2 discrete states. And it's like your porch light on Halloween. And we have circuits or switches in on-off states. And that allows us to assign coding schemes to those circuits or those switches in on-off states. And we abbreviate on and off as 0 and 1. And that's how the power symbol came to be. It's a 0 and a 1. And the 0 and the 1 are referred to as binary digits or bits. And we learned how to measure those. And we learned the 4 functions of a computer, IPOS. And we also learned about Charles Babbage and Alan Turing, which is right here, the imitation game. And we also learned about the matrix, how everything is zeros and ones in a computer. So it's a lot of really great stuff. And I hope you enjoyed this. And I look forward to seeing you next time. As always, reach out to me if you have any questions or need any help with anything in the class. See you next time.